This is the talk on generics in adulthood. I want to start by doing a land acknowledgement. The land where I stand belongs to other nations: Potawatomi, Miami, Kaskaskia, Oceti Sakowin, Kakapuy, and Peoria. So I want to acknowledge that this land belongs to them. My name is Saleem Siddiqui. I'm in various guises: a technologist, conference speaker, obviously, writer, blogger, but obviously what I do most is help solve problems, business problems using technology. And if you want to, within reason, stalk me digitally, here are a couple of ways that you can do that. Again, last year I published a book. If you do read it, let me know how you liked it. If you didn't like it, then maybe keep it to yourself. Okay, so we're here to talk about generics. Generics in Java are 18-year-old. Well, technically, they would be in a few days on September 30th, which is the 18th anniversary of JDK 5, when they were officially made a part of the language. If they were a person, they would be treated like an adult. So that's how old they are in the Java landscape. There are many developers for whom they have been a part of the language since they started programming. So life before generics, for perhaps many of us, may I say most of us, is not something we contemplate. But there are things that are even older than generics in Java that were not a part of the language originally. So reflection was added later, the assert keyword, strict FP as an annotation was added. And of course, many packages were added. Java's packages have grown beyond bounds over the last almost 3 decades now, but we're going to ignore that. We're talking about enhancements to the language, the core language, as opposed to additional libraries. But even there are things that are older than generics. In fact, the strict FP keyword was added and then deprecated since Java 17. So it's not like generics have held sway in terms of the most significant, or perhaps certainly not the only addition to the core language. Other things have come, and as we see, some of them have come and gone. However, why do we need generics? Well, the reason we need generics is because we want to answer questions that are semantically sensible, and we don't want to answer questions that are syntactically correct but semantically meaningless. How does the color blue taste? Grammatically a correct sentence. It's not made of nonce words. It follows the laws of English grammar. But it doesn't make any sense to try to answer that. Notice this question is different in kind from how does, of course, licorice taste? Or even, how does dirt taste? Those questions are obviously, they're all semantically correct. The last two, they're all syntactically correct. The last two also happen to be semantically correct. For example, if you were to render the last two questions, or the general question of tasting something, this would be the function of taste function, which takes a parameter of blue. Now this is evidently or superficially unanswerable as in unevaluatable, compared with if you ask the taste of licorice, you could return an array containing the taste. Even if you ask for taste of dirt, you could throw the appropriate exception that, hey, there may be a taste associated with that, but I'm going to throw an exception. It makes sense, but it doesn't make any sense to ask the taste of a color. Because, again, coming to language semantics, color is an attribute, a class, if you will, with which we do not associate the property of taste. There's no semantic equivalence between those two concepts, and therefore the first method call, if you will, or the first English question, is inherently different from the second and the third. We don't want to answer that. We don't want to entertain such questions. That's why we need, essentially, generics for type safety. There are certain questions that are semantically meaningful. We should answer them or attempt to answer them. There are others that are just not. We don't want to entertain those questions. In our compiler sense, we want to essentially outlaw them by making sure that the compiler complains or loudly tells us that, hey, this question, while you wrote in a seemingly legal Java statement, this doesn't make any type sense. So type safety is what we are looking for. Now, type safety is not by itself the only thing we need. Now, this is a sensible question. If I make something with lots of honey, how would that taste? Now, notice the difference between asking for the taste of a specific thing versus the taste of something abstract. If I make anything with honey, how would that taste? That is a sensible question. We want to be able to answer that, even though the thing that is being baked or the final thing is in a very real sense abstract. But we can conceive of an answer for that. So we do want polymorphism, things that are made with honey. Could be a wide variety of things, but we want to answer the question of how would they taste. But we don't want to answer the question of taste for something like color. So there is a distinction there. So polymorphism we'd use all the time in Java, obviously. I mean, none of these lines of code are a surprise to anybody here. You can create the first line as a legit line. It will evaluate correctly, as in it won't raise an exception. You create a new object. You try to equate it with hello world, which is a string. And of course, the answer from the assert keyword would be false. We all know that the signature of the equals method inside the object class is it takes an object. It doesn't take a string, but polymorphism works, and we can substitute a string for an object. Strings are objects. In Java, everything is an object. So you can substitute a string real-time value for a method signature that demands an object, right? So we are all familiar with that. That is one kind of polymorphism that's called subtype polymorphism, wherein a method signature demands a certain type, and you provide a subtype of that type, which because of the natural nature of the is-a relationship is a legit question. You cannot provide a supertype because obviously it doesn't work. It's not a symmetrical relationship. Every string is an object, every object is not a string. So when an object is asked for, you can provide string, or for that matter, any other object. It's a legit thing, and this is allowed. However, this is not the only kind of polymorphism that we have. There is another kind of polymorphism that we also use. It's a little bit more subtle. So let's see some examples of this. So if you look at the operator like plus, others like it. All of these statements will evaluate to true. So if you add two numbers, you get another number. If you add a string and a number, Java coerces both of them to become strings, and the answer is different. If you add a floating point number and an integer, you get a floating point number. If you divide two integers, the answer you get is automatically integerized, if you will. Versus if you make one of them a floating point number, the same operation gives you a different result, because Java reinterprets the meaning of that slash. The slash is essentially an operator, but you can think of it as a function. You can implement that as a function if you like. So that function's behavior depends upon its operands. And you can have even complicated statements like that. You can apply logical AND to character classes, then subtract from that, and you will get an answer. So what's going on is the same operator plus or slash or the logical AND taking on different meanings because of the operands it is operating upon. The behavior is changing, right? It's not just that you can supply a string for an object, but the behavior is the same, whatever is inside objects to string. That's not what's happening. The behavior is changing depending upon what operators you're providing to the same operator or function. But it's not like anything goes. So obviously, if you try to add 1 to a new object, you'll get a compiler error because there is no definition on how to add the numerical 1 to a new object. If this was a string 1, it would evaluate because then the right-hand operand would be stringified with the toString method. So there is some compiler is doing some things, is saying, hey, that last statement, that's not valid. Like, that's a nonsensical question, 1 plus new object. But if you have a string of 1 plus new object, that's a sensible question. So notice how even in something as simple as that, the behavior of the plus operand is both very subtly changing and also showing up as a stop sign when you try to ask a completely ridiculous question, right? So what is this? This is parametric polymorphism. This is not the same as the toString method can be called with any object. This is the behavior of the same function or operand. It's the same thing for our purposes. Materially changes based on the arguments you give it. And of course, there are hard boundaries. You can't give it ridiculous arguments to make a semantically incorrect sentence. That would be rejected by the compiler, right? So that is parametric polymorphism. So obviously, we want type-safe polymorphism. That's what we desire. And we want both kinds of polymorphism. We want subtype polymorphism, and we want parametric polymorphism, right? So we started the question, why do we have generics, or frankly, why do we have many of these features? We need these things in a type language like Java. And it turns out there's tension between these two things. So life is not all hunky-dory. You can't have your cake and eat it too, as they say. When you want all of these things, there's tension between these things, and that's where some of the problems with not just generics, but other features in Java come in. So let's take an example, or look at an example. To surface some of these problems, what you need is an object that is the type of two different classes. So you need an object that is a type of class A and a type of class B. Now you might be wondering, in a singly hierarchical language like Java, singly rooted hierarchical language like Java, it's not C++, how is that even possible? And of course, I don't necessarily mean interfaces, I actually mean types. So you could conceive something that extends a class and implements an interface, but I really mean something more broader than that here. I mean an object that can be the type of any class. Now you might be wondering, hey, which object can be a member of any class? Well, if you extend the meaning of the word object, there is at least one that is a member of any class known in Java, and that is null. Null is of any and all types. It really, from a type standpoint, it's like an amoeba. It can take whatever shape its surroundings are, and it will be type checked. And we'll see the implications of this throughout this conversation. So this is what gives rise to method is ambiguous errors, which if you have seen, they are an annoyance outside of generics. That's an outcome of the fact that null is of any and all types in Java, gives rise to that. It's very easy. Apologies, this is a little bit small font, but really what it is, this code, which you can run in JShell, or of course you can compile and run it, same thing. So one-line class, it has two methods, same name, show, different parameters, which are not related by any superclass or subclass. So one show takes my class, and one takes a string. And of course, string and my class have nothing in common. They are different, distinct classes. And when you call new my class with show of null, you get this error, because the compiler is trying to disambiguate which method I should call, and both match, because the argument null doesn't give it compiler any clue. Null is of all types. So the compiler is confused here. It's going to throw up its hands and say, hey, you asked me to invoke some method, and I'm not even sure which one, so there's something wrong. Ambiguous method is ambiguous. Reference to show is ambiguous. Very easy to reproduce this in Java. But of course, you can say null is a special case, right? So why am I beating around that particular bush? So for anything more substantial than that, getting outside of the realms of a null, we need a little bit more detailed hierarchy. For the remainder of this talk, I'll use this self-evident class hierarchy. There's a shape class and then different subclasses, triangle, circle, and rectangle. Some behavior is common. All shapes can be drawn, and of course, some behavior would be different. A triangle has 3 sides and 3 angles, and circle has a radius and a center, et cetera, et cetera. So we can easily conceive this is a useful and self-evident hierarchy that we'll use for the remainder of this talk. So if you have that hierarchy, how would you implement parametric polymorphism? You would have a class shape, and let's say you want to define a concept, are two shapes similar? That's a geometric concept. Two shapes are similar. For example, all circles are similar because they really are the same shape. Rectangles are similar when the ratio of their two sides are the same. Triangles are similar when all 3 angles are the same, regardless of size. So there's a notion in geometry, in Euclidean geometry, that defines what similarity is, right? So let's say you want to say every shape should be able to determine if it is similar to, not identical to, but similar to another shape, right? That's a valid notion. So you might write a method like similar shape S. Now, the problem is Java's general rules of subclassing do not allow you to change the signature of the method in a subclass. You cannot say public Boolean similar circle C as the argument if you want to override in the circle class. You have to stick to the signature. In fact, and I strongly advocate you use the override annotation, because if you didn't use the override annotation and you defined a method called similar with the circle, it is not considered an overriding method. It's just an overloaded method at that point in a subclass, different signature completely. That's not what overriding means. What we want to do is every class defines this notion of similarity differently, but every shape subclass knows what similar means in its context. That's our intent. That's what we want to encode. But we can't do that by changing the signature. Now, if we were to implement this, it's very obvious, you might want to start by excluding everything that's a non-circle, right? So circles cannot be similar to non-circles. That question doesn't make any sense. So the first thing the circle class implementation will do is, if S is an instance of circle, then figure out if similarity is there. Maybe the answer is always true because all circles are similar. But if it's not a circle, the answer is patently false, which means you gave me a shape that's not a circle, there is no question of similarity. That's how I would implement it, right? I mean, you can conceive that that's how we want to implement it. The problem is, if you implement it this way, you have entertained the question, when is a circle similar to a square? You have to write written code for that. The answer would be false. It will always be false, but you will give an answer. Now, I submit to you this question is just as ridiculous as, what is the taste of color blue? We can decide. I mean, this is a question on which reasonable people can disagree, but you might want to say, well, this notion is not even defined in geometry, the similarity of circles and squares or circles and triangles. This is a ridiculous notion. Why are we writing code that answers false to that? Why are we not rejecting this semantically senseless question outright? As in, why are we not letting the compiler prevent it, as opposed to writing code that returns false for it? There's a distinction there, right? So you can do that, obviously not without generics. So this is where generics come in handy. So if you were to do that using parametric polymorphism in generics, you would have to provide a generic class shape, which took in some type parameter s extends shape, and then the similar method in shape would just use the generic type parameter s, and then the circle would extend shape with its own type. So circle extends shape circle, and notice, now you can change the signature of the similar method in circle to actually say, a circle is only going to try to guess similarity with other circles. The type enforces that. You can't even call this method with a triangle or a square. The compiler will complain. And then, of course, the beauty of this is, in the implementation, you don't have to check for types, and you don't have to return false. You just look at the circle that was given to you, and you determine the notion of similarity in a straightforward way. Now, if that particular one is rooted in a hierarchy that's not deep, if you were going to have a deeper hierarchy, you want to make sure that your generics allow for that. So for example, if you have a hierarchy shape, then rectangle extends shape, and a square is a very special type of rectangle with all sides being the same. So all squares are rectangles, but not all rectangles are square. That's a geometrically correct statement. If you want to code that, you might have a hierarchy like that. Then you would need to make sure that your rectangle class kept the generic going forward with a lower upper bound. So as they say, so S extends shape for shape, but R extends rectangle for rectangle, and the rectangle class, of course, extends shape. And then the rectangle can implement its own notion of equality, probably by making sure the ratio of the two pairs of sides was the same. And the square would extend rectangle, and of course the square would be similar probably to any other square, because all squares are similar. So you can get that kind of multi-layered hierarchy. You just have to make sure that you don't fix, for the intermediate classes, the type argument. In this case, is R extends rectangle. Right, so that's all fine. We haven't looked at collections yet, but probably the biggest use case for generics in Java is obviously the collections classes. So we want type safety in elements of a collection, and that's what generics give us. Now, why do we want type safety in collections? Because we want to avoid this. Just because something fits doesn't mean it actually belongs in that collection. Right? So we want to avoid scenarios where you have a collection, you open it up, and something comes out of the collection that really doesn't belong there. So you want to prevent collections that somehow have been tampered with and something that doesn't belong there has been shoved in it. So generics were added to the language after collections. Collections came in JDK 1.2. So we have those what are called raw collections. So this is again some JShell code. You can define a new array list, no generics there, and you can add the string A to it. You get a warning because it's a raw collection. Anytime you do anything to a raw collection, you'll get a warning because raw collections, while there for compatibility and backwards compatibility reasons, they're discouraged. So it will do it, the compiler will do it, but it will say, hey, uncheck call to add E as a member of a raw type. And then you can try to add, you'll get these warnings, you can try to add something else, like a big integer.1, you'll get another warning, say, hey, you are trying to add something to a raw type. But the thing is, if you try to type at the end, it's got all those things in it. I mean, it's almost like it's gonna complain and moan about it, but it's gonna do it at the end of the day, because that's what's needed for backwards compatibility, right? Your raw collections will work kind of like they were always supposed to work without any type checks, but they will complain anytime you try to modify them because, of course, as we said, they don't give you that kind of uniformity that what comes out is what, it has some expectations of norms. Anything can come out because you can shove anything in. Contrast this with generic collections. So now here we have an array list with a generic type of number, which is the superclass of integer and big decimal and big integer and all of those things. So it starts off looking the same. It's just empty collection. We add a big integer, and we can add an integer to it. So collections elements are covariant in the normal way, right? So if I declare a collection of type number, I can add anything of number or its subtype, right? So I can add a big integer, I can add an integer, that's fine. No warnings, no problems, straight up, right? And of course, if I try to kind of get cutesy with it, try to add a string, I get an error here. There's a difference. It's not a warning, it's an error, and it just won't happen. Obviously, this is a J shell, but if you were to compile this, you'll get a compilation error. The previous one would be a runtime error, or runtime compile time warning, and a runtime, some kind of class exception if you just went with raw collections. Here, it will be a compilation error if you have a collection of numbers, an array list of numbers, and you try to shove a string. It just won't happen, right? I mean, it's just not going to do it. So that's what, of course, generic collections give you. Now, the biggest stumbling block for, I would say, even seasoned developers, and certainly for new programmers to kind of wrap their head around, is a list of strings isn't a list of objects, nor the other way around. A list of objects isn't a list of strings. And this is the notion of invariance, which we'll look at in some detail shortly. But this is probably the biggest, or perhaps the most non-intuitive things. A string is an object, so you assume a list of string is a list of object, but it's not. And neither the other way around. They have, by default, they have no relationship. They're just completely different things. They're not a type of. So here's how we can, here's why that is a good thing. So if you create an array list of number and you try to assign it to a list of object, that'll just fail. And it will just blatantly tell you that an array list of number cannot be converted to a list of objects. Even though a number can be converted to an object, a list of numbers cannot be converted to a list of objects. They are different things. However, if you wanted to do something with a generic list, how would you do that? This is where wildcards come in. So obviously, if every collection was very hardwired to one type, and we just saw a list of numbers is not a list of objects, a list of circles is not a list of shapes, then how do we have lists that have any value, have any utility that we can put different kinds of things in? Well, you have to use wildcards. So here's an example of a canvas class where you have different shapes, all kinds of subclasses of shape, and you want to draw them at some point of time, right? So there are going to be all different subtypes of shape. It's probably never going to be shape. Shape is probably an abstract class. You can't instantiate it. Some are going to be circles, some are going to be triangles, some are going to be rectangles, some are going to be squares, whatever, some subtype of shape. So how do you represent that without getting into that invariant problem that a list of shape or a list of circle is not a list of shape? So you use this notion, or notation, list of wildcard extends shape. So this, it's a notational thing. These two are equivalent. So you can use wildcards, as in the first line, list of wildcard extends shape, or you can name it. So you can say some random letter. Through convention, they're single characters, uppercase, but you can use whatever. So S extends shape and draw all list of S. They're the same. The rule here, or certainly the guideline here, is you want to use bounds, such as that S extends shape, only if you're going to use that S somewhere else. In this case, we're not, so the shorter brevity is always preferable, so you probably want to use the question mark extends shape. Because we don't have any return value. So we're going to have a list of shapes that we can print. Now, an example of where you need a named wildcard is this method copy from the collections class. Here we have typed T and then something destination where the things are going to be copied and something that's the source. Notice that the source is a wildcard extending T. Why is that? It's the simple notion that, for example, you can copy a list of circles into a list of shapes, but not the other way around. Because every circle is a shape, it is reasonable to say, here's some circles, copy them over into those shapes. That's a reasonable question or request. It is not reasonable to say, here are some random shapes, push them into this list of circles. That may or may not be possible. So the source has to be a subtype of the destination, which is what this named parameter style enforces or allows you to do. Like there's a relationship between the generic notion of source list and destination list, and the letter T allows us to do that. So here, there is no other way other than to use the letter T. Like you can't just replace everything with question marks and wildcards. So anyways, going back to our notion of draw all, we have a draw all method, which takes any list of something, anything extending shape. And the question is, can we add a new circle to it? So I gave away the answer with the red arrow. You can't. You can't add things to it. Now this may sound odd, like it's a list of shape and circle is a shape. Why can't I add a circle to it? It's the reason it's not a list of shapes, it's a list of some unknown subtype of shape. So if you try to do that, it will say circle cannot be converted to capture one because it's a question mark, so we didn't give it a letter, so that's why that's the cap #1 is Java's way of placeholder. And it says that cap1 is a fresh type variable, as in a newly injected type variable that the compiler did, and your circle, it is not guaranteed at all that it's a subtype of that. And the way to understand this is this whole wildcard extend shape. Imagine some unknown subtype of shape. It could be shape itself. In this case, every type is a subtype of itself. So starting at itself and potentially infinite depth. That's what that thing is saying. Some unknown subtype of shape. And there's absolutely no way to guarantee that the circle lies on that hierarchy. It may or it may not. Right? You could have a completely different hierarchy and some infinitely deep subtype of shape is being talked about, and there's no way to shove a circle into that collection because the compiler can't guarantee that. That's why it's not allowed. However, this is again back to the null, this is always allowed. Nulls are the things that are the subtype of everything, so even though the method says question mark or wildcard extends shape, you can add nulls to that. And the compiler passes that because it says, hey, I don't know what the class is going to be, but I'm pretty sure null is going to belong to that class because null belongs to every class. Obviously, this is probably not useful in many cases. Why would you want to add null to a collection? But just wanted to let you know how type safety works in the presence of null. This is actually going to become relevant when we talk about some of the problems that we have with generics even today. So what do we do when we want to add things to a collection? We have to use super. So when you want to have modifiable generic collections, you don't use extends, you use super. So here's an example. Let's say we want to have, this is a reasonable request, right? We want to create a new list of objects. Notice objects. And we want to add some shapes to it. Our mental model seems to be right. Shapes are objects, so I should be able to add some shapes to a list of objects. That's my need. In the second case, I have a list of shapes, and I want to use the same method to add shapes to that list of shapes. Also a legitimate request. Probably the second one is prima facie more legitimate. But they're both legitimate. So how should the add shapes method be written to allow for both of these? So here's where we use the super keyword. So add shapes can be written like this. Wildcard of super shapes, so some unknown super class of shapes. If you can imagine shape all the way up to object, it will take a list of those types, and then it will add a circle. You can add circles, rectangles, you can always add a null. I just threw that in there. Nulls are always allowed, like nulls are infinitely type safe, you can call that. But more importantly, in this signature, with this signature of a method, you can add a circle, you can add a rectangle. However you construct them, that's not important, but you can add them. This won't be a problem. Now, of course, nulls are special. What if you try to read from this list? Do you think that should be possible? Iterate over shapes. It's a list of some superclass of shape. How many people think this should be doable, this for loop? One? So it's a reasonable guess. But turns out this is not allowed. Like, here's an interesting thing. You can add things to this list, you can't read from them. Like, say what? Like, how is that? And the reason, again, is here, because you used a wildcard with super, it is some unknown superclass of shape, from shape all the way up to object, completely unknown, wildcard. So because it's unknown, it could be object, it could be some intermediate class, who knows how deep your shape hierarchy is between itself and object, and it's a list of those types. So how can you add a shape to it, or how can you add a circle to it? There's no guarantee that your circle is indeed a type of that class, because it could be an interface, it could, Java does have, through interfaces, kind of multiply rooted hierarchy of a kind. There's no way for the compiler to guarantee that you can add anything to this collection, because it's an unknown super type of shape. How can we legitimately say that a circle or a rectangle is a type of that shape? We can't, so the compiler won't let you do that. Now this annoyance actually turns out to be a very good thing. You cannot combine super and extends in the same generics declaration, and this is wonderful. Like, there's no syntactical way to say question mark, extend something, and super something else. Like, there's no legit way to say that. And that's great. Why is that great? Because this gives us a very nice de jure style of separating our concerns. Code that reads from collections and code that writes from collections has to be separated, because there's no way to write a collection that is infinitely malleable. If you want that, you might want to go back to raw types, but they come with problems. So if you want to have generics, you will be forced to separate your code that reads from collections, iterates over them probably, from code that writes to them. And that's a great thing. It's kind of nudging you in that separation of concerns direction, which, as we know from software engineering, is a good practice to do anyways. Now, that's a very special rule, reading and writing. There's a further implication of this. So for that, we have to look at the invariance, the notion of invariance. So I'm going to introduce, or shamelessly borrow from JavaScript, the instance of, type of keyword. Because I don't want to write the long sentence in these slides, imagine if type of is jarring to you, can be substituted for. Like that's really what the expanded version of this is. So this is not obviously literal Java code because it's used as a JavaScript keyword. But the idea is, in general, and we saw that already, a list of shapes is not a type of list of circle, and the vice versa. The other way is also not true. So while a shape is a circle is a shape, the second statement is also false. A list of circle is not a list of shape. We saw that already. In general, Java's collections are invariant, type invariant. You can't infer any type information or enforce any type information on collections simply by examining the type of things in the collection. It doesn't transfer over. So the notion that a circle is a shape doesn't mean anything when you're talking about list of circles and list of shapes. They are not at all the same thing, right? By default, Java's collections are like that. They're type invariant. No type relationship between different types of collections. However, when you have upper bounds, so for example, you have a list of wildcard extend shapes, they are covariant. What does covariant mean? Covariant means essentially that if when you read this, the type of relationship between collections is in the same direction as the types they're in. So is a circle a type of shape? Yes, a circle is a shape. So a list of circle is a type of a list of collection with an upper bound of shape. So wherever a list of wildcard extend shape is being asked for, you can give it a list of circles. That will be accepted, right? That's what this means. Contravariance is where this goes in the opposite direction. So lower bounded generic connections are contravariant. What does this mean is, if you have a place where a list of a wildcard super circle is asked for, you can give it a list of shape. Notice the direction here. A list of shape is a type of list of wildcard super circle. However, a circle is a type of shape. Like that relationship is going from right to left versus the collection relationship is going from left to right. This is contravariance. So now that you know these three things, the general version of that rule that I just showed a while ago about reads and writes is that you use upper bound generic collections for covariance and lower bounded ones for contravariance. So of course, you first have to determine what you want in the code that you're writing. And in the code that you're writing, you may not necessarily be reading or writing stuff. You may be doing, and comparisons are a good example. If you look at the comparator class in Java, that's a good example of how it uses upper bounds. But in general, if you have code that needs upper bounded generics, that is meaningful or valuable when you have covariance, and lower bounded ones for contravariance. Okay? So why do we need all of this? Or what is another interesting thing about generics in Java? This whole machinery only exists for the compiler, right? At runtime, there's nothing else. So you can even try that very easily. You create a new array list of number and an array list of string, and you compare their classes, and the classes are the same. At runtime, generics, obviously, as we know, don't create any new type information in the classes. There's definitely not one new class for each generic type. That would be bloated. That is different. That's a different decision in Java than compared to other languages such as C#. But that's a decision in Java. Generics, the type information only exists in the compiler. And it is, after the compiler is done, it is erased. That's type erasure. The type information that you provide in generics does not last beyond the compilation stage. Now, erasure was the great compromise. It was necessary to basically keep Java running and running Java applications not stop working. But it is a huge compromise because imagine all of this information that is available at the source code level in the compiler is absolutely unavailable to the runtime environment. In the runtime, there is no generics information whatsoever. It's already thrown away by the time bytecode is generated. So here's an example that illustrates that generics with type erasure were necessary because we have generics, we have lists and collections without generics, right? They have predated. So for example, you can have a list of strings. That's what the first line defines. If you try to assign that list of strings to a list of object, compiler will complain and say, nope, they're not the same thing. Can't do that. However, you can turn around and assign that to a raw list, and there's no complaint. Right, that's the last line. List O equals S, a plain old raw list, and you can assign it to a list of strings. It has to work that way. Why? Because there are mounds and mounds of Java code that uses and takes as parameter and returns raw types. If we didn't allow that last line, you can imagine all of that code would become immediately useless and unusable. It would start throwing the kind of errors that that middle one throws, incompatible types. Of course, that would be a huge loss. Imagine the mounds of code that was written in the first 10 years of Java before generics came on the scene, and it just is not possible. It's practically unfeasible to say, yeah, somebody's got to rewrite that overnight, literally. And that's the reason for the compromise. We need generics to have type erasure, to throw all of this stuff away, because we have collections without generics, and they have to work with collections with generics. So this is not allowed, the first one, but the second one is. Generics create no information at runtime. All of the information is erased when bytecode is generated. And the why, again, is because we need to coexist. As they say, when you come to a fork in the road, take it. So the reason we have all of these compromises is because there were a lot of decisions that were made in Java. Some were deliberate, and some of the hands were forced of the Java designers. So here's some decisions, right? So even today with JDK 19, this is from, I haven't tried JDK 20 yet, but this is from 19. If you try the -- source flag, notice how many numbers it's backwards compatible to, from 7 all the way to 19. Now 7 was released in 2011. It's actually, its active support, I think, is ending later this year, or it might have already ended. The Azul folks would know, because they're, I think, the last one supporting it. Their JDK is the last one supporting it. But still, right now, if you ask JDK 19, compiler, hey, how many backwards compatibility sources supported? We'll say 7. And the same for target. So you can today, right now in late 2022, you can write Java code, compile it as if it was written in 2011, and expect to run it as if it is run on a JVM from 2011. I mean, that's pretty sick, right? I mean, you're going essentially in a time machine 11, 12 years back and saying, I want exactly the same behavior. So that's a decision. That's a pretty long backwards compatibility notion. So that's a decision that was taken. And just historically, collections came first in JDK 1.2. Generics came later. So by the time generics came on board, there was a lot of collections had been around for 3 versions. And if you recall, back then JDK versions used to be slower. I believe JDK 1.2 came out in 1998 and 5 in 2004. So it's like 6 years worth of intellectual property that exists out there. What are you going to do? You've got to make them interoperate, right? You can't just throw that away. And of course, nulls. Sir Tony Hoare is very, I guess, self-deprecating in calling it his billion-dollar mistake. Actually, I'm surprised nobody has sued him yet, because he did admit that in a conference. But maybe his stature and, frankly, his age precludes that. But yeah, Java has nulls. And unlike languages like Ruby, which have first-class objects for nils, Java's nulls are kind of special, right? They kind of show up. They're the types of everything, as we saw, but you can't ask them anything. You can't ask them anything to throw a null pointer exception. So they're kind of this weird thing where they're everywhere, and you can't query them. So obviously, the answer to that is use optionals, another good idea that, again, you can say sadly came a little bit too late, but use optionals because nulls, as Sir Tony Hoare himself says, it's his billion-dollar mistake. So, but it exists in Java, even to this day. They are there. So a consequence of all of these decisions, there are some other decisions that have to be made. When you have all of those things, you have to have type erasure, as we just said. You can't have runtime information with generic types, because what about the older runtimes, all the way to JDK 7? And when the version 5 came out with generics, it did allow even older versions, I believe all the way to at least 2, if not all 1. So when generics were first released, there was no guarantees that the runtime supported them. So you had to make sure that type erasure ensured that at runtime there was no notion of generics. Otherwise, how would the older runtimes deal with this newfangled bytecode? So the bytecode had to look the same. And their interoperability with legacy raw collections. They had been there. They were part of a library for a good 6 years. You couldn't take them away. Java has this habit, this practice of never taking old classes away. So they're there. What are you going to do with them? You can't prevent developers from writing code using raw collections. So these decisions are almost foisted upon you once you accept the previous decisions that I saw. So the combination of these things is there's some interesting behavioral quirks that have happened. So this is from Gilad Braca's original paper in July 2004 that he wrote about generics. Very, very readable one, and I definitely recommend all of you should, frankly, bookmark it and read it periodically. It's a very good paper on generics in Java. There's this line in it: if your entire application has been compiled without unchecked warnings using Java source 1.5, recent as of then, but I would imagine you could go at least as far back as 7 today, it is type safe. That's a direct quote from that paper. I would humbly submit that if by type safety it is meant no class cast exceptions at runtime, this statement is demonstrably false today. You can have a class, because of all these decisions that were made and the weird interoperability and interplay of those decisions, you can write a Java program with no warnings at compile time and yet class cast exceptions at runtime. If you're curious, here's a paper that I also strongly recommend. It was presented at the UFSLA in 2016 by Nada Amin and Ross Tate, and they talked about the unsoundness of Javas and Scalas. Very similar language, obviously, runs on the JVM, more functional in nature, but essentially from a type standpoint, more or less identical. They pointed the mistakes, or the consequences of the mistakes that have been made throughout the years and decades, specifically, as the subtitle says, the crisis because of null pointers. So here's a code from that. I would strongly recommend you read the paper to see how this class works. They have a lot of examples in that, to the immense credit of JDK authors and all of them who are out there. I salute them. Some of the problems in that paper no longer compile, even in the last 5-6 years, since 2016. This one still has that trait that it has no class cast, it has no compile time warnings, yet it throws a class cast exception at runtime. So I'm not going to try to explain it. There's a lot of detail in it that you need to understand. I'm going to just briefly, in the interest of time, define the quirks and the things in it that give that behavior. So number one, it has this curry class, currying, as you might know from basic software engineering principles, or if you've done a language where that's a first class principle like Haskell. It's essentially reducing a function's type to a more constrained type. So this one, this class, for example, is typed to a type B that extends A, and then it curries that return type to A, okay? So there's a lot of gimmickry going on here. Obviously, to surface the problem, you have to use some gimmickry. Here's the interesting, one of the two things that are really curious. All of it is curious. Notice there's a function called upcast. It takes a constraint variable. What do they do with that variable? Absolutely nothing. This one is there, the constraint variable is there, not for its variable's value, but for the constraint type B. It extracts the B type for the compiler's benefit out of that constraint, and then creates a new curry object with that type, whatever that type might be. It actually doesn't use the constraint variable, it just uses the type argument. One of the gimmickries in here. Then here's a constraint class. Notice that this class only exists for the purpose of typing, has no behavior. Open curly, close curly right there. But here's a constraint class B extends A. And here's a coerce method, kind of the magic coordinator of this. It takes a constraint and declares its type very niftily to some undefined supertype of B. Doesn't really care about its value. In fact, the null is also very judiciously placed because guess what? Null is every type. In fact, null is the only value that will suffice or will be allowed by the compiler on the right-hand side. Nothing else will suffice. So it creates a constraint and gives it to the upcast function, knowing full well that the upcast function doesn't need the null. It needs that type information attached to that variable. And if you run all of this, basically when you create a bind with a string and try to use it to coerce a 0, which is obviously an integer, you get this. You get the dreaded class cast exception at runtime, despite there being no compile time warnings about classes going amok. So this you can compile today with JDK 19 and get this result. Yes, very contrived piece of code geared towards surfacing this problem within the JDK today, but legitimate Java code nonetheless. So what does this tell us? That because of type erasure, the runtime has no recourse but to throw an exception because all the type information is lost. The compiler threw it away after satisfying itself. So this statement, which is also from that paper, this I can get behind. The type safety and integrity of the Java virtual machine are never at risk, even in the presence of unchecked warnings. That, I think, is fair, because a class cast exception that was thrown in this case, guess what that is? A class cast exception is essentially the last safety net, right? Because what is the ultimate problem if you were to have type mismatch, if you were to access something of a different type? You would be accessing parts of the memory that you have no business accessing. You would be calling something type A and accessing its attributes where it's really type B, and all hell will break loose, right? Because you could read parts of the memory based on the memory allocation of objects of type A and B, and that would be completely bad. Overrun pointers and all those kind of things. That is not allowed by the runtime system. So this statement is actually, I believe this is still true, that the JVM is never in risk. The worst thing that will happen, as we saw, you'll get a class CAS exception, your program may crash, but you won't do the ultimate bad thing, which is reading memory you're not, or writing to, which probably is even worse, that you have no business reading or writing to. That won't happen. But the earlier guarantee we saw that if you don't have any type warnings, your code will not throw class CAS exceptions. That is still to this day an unrealized dream. Like you can craft programs that pass the compiler, but throw class CAS exceptions, even with the modern version of Java. Now, what about arrays? So arrays are interesting because you can use them with generics, but you don't have to because they encompass both things. The fact that they are a collection and the fact that they're typed right there in the name, right? So a shape array is an array of type shapes. They are naturally covariant. In a shape array, you can have any shape or any subclass of shape. So you can use arrays, for example, if you wanted to. So for example, that add shapes method that we saw earlier, you can write it with arrays, and it'll work exactly the same way. Obviously, you'll have to, because arrays are, the sizes are fixed, memory allocation, the way Java works, you'll have to create a new one, but you could certainly do that. Now, you can add a new circle to it. You can even do what we couldn't do with generics. Now, because this being an array, you can read and write from it at the same time. Now, whether that is good from a separation of concern standpoint, that's a different debate. I earlier said that collections kind of force you, generic collections, to do either reading or writing. I still stand behind that. But arrays don't force your hand. They are there. They are typed collections of things with covariance, with type information. You can read and write simultaneously in the same method if that's what you want. There is no special machinery, no special syntax needed. So you can do that. This is legit here. However, they're not a panacea, right? So here's a problem with arrays. You can still get into that contravariance problem. So you can declare an integer array. You get that. You can assign that to a number array, that line, number array an equals ai. And then you try to add a big integer to it, and you'll get a runtime array store exception. Array store exception is the array equivalent of the class CAS exception with classes. Basically, you're trying to shove something that doesn't belong. So this is a runtime error. You won't get it at the compiler level. There's no answer there, right? This is again from that paper by Nada Amin and Ross Tate. The problem is that Java, along with many other major industry languages, is extremely large. Java has grown, and I don't mean the packages at all. I don't mean that at all. That's just libraries you can use, and they come in, well, they never go, but they keep coming. But you can use libraries from anywhere, from any repo that you want. The problem is the core language has grown, and it's extremely large, and mathematically verifying that all features of it work is pretty close to impossible. Now, why is this? I would say that you can try this with anything with many features. This is a picture from my kitchen. When I open this particular drawer, I can't open the oven door. Anything with a lot of features, you'll see this interplay between features that make them impossible to use. Try this exercise in your own bathroom or kitchen. Something with a lot of features, like drawers you can open and things you can hang and ovens that you can turn on, but please do it safely. You can always find a spot where you try to exercise two features simultaneously and you can't. This is basically the problem of too many features. You can test each feature. Yep, this drawer opens, the oven opens, but does this both open simultaneously? That is the problem of the overlap and the nonlinear problem of complexity of too many features in a language. Now, just real quick, because I did promise I'll show you Go. Go is a new modern language, and its generics are completely different. They are essentially an alias for a combination of types. So here you can declare an interface. Go does have interfaces. And you can say the number interface can be either int64 or float64. And then you can have methods that take number as the second parameter, right? So the v is a number, which means at runtime, it can be either an int or a float. And then you can operate the same way. For classes, Go actually is even simpler. So you can have an interface called draw. And Go has no explicit subclassing. It's actually kind of interesting. It's all implicit. So because the interface says it should have a method draw, any structure, any type that implements draw is implicitly a shape. You don't ever declare in Go that, hey, I'm a circle and I implement shape. Unlike you do in Java. In Go, You just say, here's a circle. It implements draw. So therefore, it must be a shape. You don't ever say that, but if you didn't do that, you couldn't substitute it. And then you can write either of these two methods. They're virtually identical, and you would implement them the same way. The first one uses generics. Syntax is somewhat similar to Java's with square brackets. And the second one does not. In fact, so you could say if it goes generics, you actually don't need them. They are a shorthand for a combination of types. Different language, different set of problems, different solution, and different implications. So what does that leave us with? There's no silver bullet to avoid all kinds of runtime type errors. There's just none. You can try your best. You can, of course, rely on the compiler to not give you any compile time warnings. If you get compile time warnings, address them. But there are no guarantees. You probably will not write a contrived program like the one I showed you, but you do realize there's always a chance that despite no compile time errors, you get runtime class cast warnings. Now, the reason why that is a hard problem is, I think, best summarized by this classic question that Lewis Carroll posed in his book, Alice in Wonderland. Why is a raven like a writing desk? Now, he did answer that question, but only in the second edition. In the first edition, I think it's a Mad Hatter, or it's probably Lewis Carroll speaking for himself, saying there is no answer to that. And therein lies the dichotomy, right? Is this a semantically meaningful question that we should try to answer? Or is this a nonce question that we should not? Reasonable people can have differences of opinion about that. And reasonable people will come to different conclusions about how they want to approach this question and the code equivalents thereof. And therefore, you'll always have this challenge. Should I answer this question? Should my code entertain this question and give a response? Or should my code say, no, class cast exception? You're trying to equate two things that don't go together. Thank you. Okay, any questions? We do have a few minutes. Great, I either nailed it or I lost everybody. Yes, go ahead. I'll walk close to you so I can hear it, and then I'll repeat the question.
Since generics have been out for so long now, are there any plans to actually finally make them available at runtime?
Yeah, good question. So the question is, generics have been out for so long. Are there any plans to make them available at runtime? There is a movement called reified generics. Look it up. Actually, it's not even that new. I think the first papers came out in 2006, like 2 years after generics came out, part of the language. So exactly that notion, that can we not please have reified generics at the runtime so that we can exploit, of course, reflection, and people get all drunk on reflection. Imagine it would be available via reflection, and you could look it up and do probably all kinds of stuff that you shouldn't be doing. So again, the double-edged sword, right? So the plan is there. I don't know personally. I mean, I would actually be curious, our friends out there, Azul and others who actually build the JVMs, what do they think? But at least that I know is for, 16 years now. There's at least has been a movement that why erasure? C# doesn't do it. Other languages, C# also got generics later, but they are available at runtime, does it differently. So at least there is that movement there. I couldn't say if that's going to become part of the JDK. I would venture to say it's going to be a pretty seismic move, as in, I'm certainly not as smart as the language writers, but it would be hard. I'm trying to think of how would you do it in a backwards compatible way, or would you immediately reset the -- source and -- target flags to say this version onwards and nothing from beyond that? Maybe there's smarter minds than mine are thinking on that very problem. So there's a movement there. I don't know if that's coming in any JDK near you, okay? And give me your email, you'll get a copy of my book. Any other questions? Okay, well, thank you so much for showing up. Hopefully you enjoy the rest of your conference.